say, so how does volumes differ from area, kids? If I told you this shape right here I'm holding has area, where's the area at? It's the outside, right? So how does area differ from what we're going to talk about today, volume? If I'm talking about volume of this same figure. Volume is what's inside. We want to measure how many cubes it would take to fill this up. Okay? So how many cubic units it would take to fill something up. So the idea is this. We're going to start looking at volumes. And again, guys, volumes, always talking about number of cubic units inside, okay? Number of cubic units inside of a figure. That's what volume means. So we're going to start looking at volumes of prisms and cylinders, okay? Give me an example of something that's a prism. A what? Well, I think you're thinking pyramids, okay? Okay, all rectangle sides, yeah. Is this a prism right here? Kind of like a box, right? All sides are, well, not necessarily equal, but they're all going to be flat. And then two bases are going to be the same shape and congruent to each other, congruent parallel to each other. Okay, do you guys know what a cylinder is?
Yeah, a flat circle face.
Okay. Is there an example of a cylinder in this room anywhere? Kind of like my cup there, yeah. Okay. How about this right here? These lights right here. Isn't that a cylinder right here? Okay. All right. What are the shape of the bases on a cylinder, kids?
Circles.
Circles. Okay. So I think we have a pretty good idea of what prisms and cylinders are. So the question today, volunteer to read that for me.
How can you find the volume of a prism or cylinder that is not a right prism or a right cylinder?
Show you what they're talking about here, kids. Imagine a bunch of pennies. Okay, you guys got all your pennies? Okay, if I stack them up straight, it kind of looks like this. It looks like a pen that's stacked up straight like that. Okay. Now there's a tower that's somewhere, and they call it a certain tower. You know what tower I'm talking about? Ever heard of the leaning tower of Pisa, right? Some people call it, like my kids' home, the leaning tower of Pisa. Okay, but we're going to talk about things that are kind of slanted like that a little bit. Okay, and I'll show you what that means here in a bit. But we're going to start talking about stuff that's not necessarily a right cylinder or a right prism. I'll show you how to find those volumes. Okay. So today, guys, goals: classify solids and find volumes of prisms or cylinders. All right. Okay, vocab-wise. First word up there, polyhedron, kids. It says a polyhedron is any solid, so it's three-dimensional, that's bounded by what?
Polygons.
Polygons. All sides are a polygon. Can't be curved. They all have to be flat polygons. Okay, so there's an example right here. By the way, what kind of prism would this be? What shape is the front and the back? Trapezoidal prism. Okay. A face for a polyhedron, kids. Face is simply a what?
Shape. The top.
Well, it could be the top. Actually, how many faces does this have if it says it's a flat surface of a polyhedron?
6.
Has 6. There's a front and a back, a top and a left and a
right.
So a face is simply a what, kids? Anywhere we have a flat surface, that's considered a face. An edge, I don't need to get too technical with this. I think you can see what an edge is. It's where two faces do what? Join or meet. Okay. A vertex of a polyhedron is a point of a polyhedron where 3 or more edges meet. So this point right here is formed by this edge, and this edge. So how many edges form a vertex? 3 of them. Okay. Volume, we kind of talked about a little bit. It's the number of cubic units contained on the interior of the solid. By the way, rectangular prism. You guys recall how to find volume? Okay, so right here, anytime we're doing volume, what do we want to be true about these 3 units? 6 feet, 4 feet, 3 Anytime we're trying to find volume, what do you want to make sure you have established?
For the same measure.
All your units are in the same unit, right? All your measures are in the same unit. Okay? Then this is kind of an important one right here. This says Cavaliers Principle. Okay, this is what I want you to kind of think about. Any of you guys have a slinky at home?
Yes.
I do.
You know what a slinky is, right?
Yeah.
You take the slinky and set it down. What shape is it form?
A cylinder.
But if you take that slinky and kind of start sliding stuff over, can you slant it a little bit but have it hold the same height? You know what I'm talking? How many have done that? Take the slinky and it kind of slants it a little bit.
And I don't think it's
You're pushing on it at the top and it kind of slants itself. You know what I'm talking about, right? Okay? Here's the deal. Cavaliers Principle states this. If two solids have the same height and same what?
cross.
When I talk about cross-section, when I take a knife and cut through here, what shape is formed here in purple for this cube?
A square.
Okay, but this is kind of like a square slinky. We're going to take it, we're going to twist it, push one side over. What's true about this shape right here again, kids? It's still a what?
Square.
It's still a square. It's the same, but are these the same exact shape right here now?
No.
But they still have the same cross-section. If I would cut through here, this purple base right here, this purple square would be the same as this purple square. Therefore, Cavaliers' Principle says if you have two solids, same height, same cross-section, we better read the next page. Same cross-section, all area at every level, then they have the what?
Same
Same
volume.
Same volume. And we'll look at some examples like this here in a little bit, okay? What's the name of that principle?
Count 3.
Simply states, if you have one that's standing straight up and down, and then one that was maybe slanted like this, but it still had the same circles there, it would still have the same volume, okay? And then we're going to talk about similar solids. Similar solids are two solids of the same type with equal what? Ratios of corresponding. Okay, so if I tell you this right here, if I tell you the height of this is, oh, I don't know, 4, and maybe the height of this one is 5, and if I tell you the distance across here is, I don't know, 2, anybody have a guess what the distance across here would be?
3.
Not 3. How does 2 relate to 4 here?
Oh, 10.
So how much would you have here? 2.5. Yep. Okay, I'll tell you what we're going to do here in a little bit. Okay. Vocab-wise, I don't think there's anything in there that's too pressing. I think you should be in good shape. Okay. Guys, the first thing we're going to talk about are types of solid. We have some polyhedrons up here, and we have some that are not polyhedrons. Okay. This polyhedron right here, this is considered a polyhedra. This is a what?
Amen.
The first one is a. Furthermore, what kind of prism? Rectangular prism. It's a polyhedron because all the sides are what? Flat. Okay. This here would be a pyramid. All the faces meet at one point. Okay. Tell me why this one here. Tell me why right here. Why aren't those polyhedrons?
Because it's not a flat surface.
The surfaces are not flat. They're actually what?
Rounded.
They're rounded. Okay. They're rounded. Some of the surfaces are rounded. So what we would say is this is a what? This is a, and this is a what? Okay. So let's jump into example 1 here quickly, kids. It says classifying solids. First of all, tell me whether it's a, is the first one a polyhedron? Yes or no?
Yes.
Yes.
Why?
Because it has flat sides.
All the sides are flat. Now, is this going to be a prism, a pyramid?
You got a pentagonal right here.
Yep. It's going to be a polyhedron, so I'm going to write down yes, first of all. Why is this a pyramid, guys?
Because all the triangular faces meet at one point.
All triangular faces meet at one point up here called the vertex. So I'm going to call this, what's the bottom base here?
Pentagon.
Pentagonal pyramid here. Pentagonal pyramid. Okay. How about part B? Is that a polyhedron?
No.
Why does it fail a polyhedron test?
It's half a sphere.
It's a hemisphere. Okay, and are all the sides flat or are some of the sides rounded? There's some rounded sides. Not all sides are flat, so I'm going to say, is this a polyhedron? The answer is what?
No.
No. Okay. How about part C? Is that a polyhedron or not?
Yes.
Okay. Second question. If it's a polyhedron, is it a prism or is it a pyramid?
Prism.
This one is a prism because all the faces don't meet in one point. So which two sides would classify that prism? What shape would classify that prism, I guess?
Hexagon.
Yeah, a hexagon. The two sides that are parallel and congruent to each other, front and the back. Hexagon, 6 sides, right? So hexagonal prism here. If I ask you guys to determine if something's a polyhedron or not, can you do that? And if it is a polyhedron, can you identify it or classify it for me? Okay. Looking at the shape, I think it's pretty simple, all right? Okay, so let's jump down here to our core concept. This is a pretty big idea. Core concept. I need a volunteer to read the core concept for me first.
The volume of a prism is B equals BH, where B is the area of the base and H is the height.
Okay, so when we talk about B, B is always the area of my what? Base. What shape is the base down here? In this case, it's a square, so we would find the area of that square down here and then multiply it by its what?
Height.
Now notice right here, what's true about the heights right here of these two?
They're the same.
What's true about the bases?
They're the
Same.
So even though they don't look exactly alike, what's going to be true about my values?
They're the same.
What's the name of that principle?
Cavaliers.
Cavaliers Principle. Okay, so let's talk right here. Let's jump to example number 2. Finding volumes of prisms. Example A right here, kids. I'm going to size this down quickly. Okay, first of all, kids, we need to identify the prism. Now, up here on the board, they do a pretty good job, and especially when you see it in your assignment, they do a pretty good job. Notice the shade right here of this. What shape is this?
It's like a darker.
The darker green. The darker shade is typically your base in all of these, okay? I guess the question would be, what kind of prism is that?
Triangular.
It's a triangular prism, right?
Right triangular prism.
Okay, so when we talk about bases, the bases are going to be a certain shape. So in this case, I'm going to put a capital B right here and say my base is a triangle in this case, all right? You guys see that triangle in green up here? It's shaded in green right there. Okay. How am I going to find the area of that triangle?
Base times height. Half.
Okay, so half of base times height. So it'll be 1/2 times 5 times what?
8.
Okay, so the area of the base is half times 5 times 8. Let's see.
20.
5 and 8 is 40. Cut that in half. Area of the base is what? 20. Okay. So when we talk about this right here, I'm going to put a B in the front here. I'm going to go ahead and say, in this triangle right here in green, this was the area of my base. Now, heights are funny. When it comes to heights of prisms, anybody got to guess what the height is? It's 3. The height is defined as the distance between the two sides that are parallel and congruent. If you think about this, you said this is what kind of prism?
Triangular.
So the height is going to be the distance between the two triangles, the one in the front and the one in the back. Okay, so the height is always the distance between the shape that names your prism. So in this case, my height is where, kids? Well, it's right there, isn't it? So isn't the height equal to 3 here? So what's that make the volume? Area of the base was what? Height of the prism was, and maybe I should take a time out and back up, but I should probably check all my dimensions. Were all my dimensions labeled with the same unit? Yeah, so we're good there, aren't we? So I'm going to say my volume equals what times what here, kids?
20 times 3.
20 times 3, which is
60.
60. Centimeters was the linear unit, so what kind of centimeter, kids?
Cube.
Cubic centimeters. You put a little 3 out there. What's the volume of that, kids?
60.
60?
Cube centimeter.
Cubic
Centimeter.
centimeters. Okay? You guys are going to talk me through the next one. We need to find the volume of certain kind of prism. Anybody got to guess what the name of that prism is?
Trapezoidal prism.
Okay, so let me ask this question. Think about top and bottom, left and right, front and back. Top, bottom, left, right, front and back. Okay? Top, bottom, left, right, front, back. Which one is my base? In other words, where are the shapes exactly the same to each other and parallel to each other? Top, bottom, left, right, or front and back?
Front, back.
Front and back. In the front here, I always like to put an outline around my base all the time. So I'm going to say, okay, this is my base because this is the side that is the same as the opposite side and parallel to it. Okay, so this is where my base B is. It's up front. So to find B here, kids, what kind of prism is this again, kids? What shape did I outline there?
Trapezoid.
Anybody recall the area formula for a trapezoid? I'll write it down for you. You guys remember this? For a trapezoid? Give me some sort of science you recall that, yeah? Okay, so to find the area of that base up top there, this would become 1/2. What are your two base lengths in the trapezoid, the two parallel sides? Yep, 4.4 and 5.6. So 5.6 plus 4.4, and then times the height of how much, kids? What's the height of that? Isn't it 2.5 in that trapezoid? Again, we're looking just the base. We're looking at just one side first to find the area of that base. Okay? Everybody understand my mess that I have up there value-wise? Okay, run that. 5.6 plus 4.4 is?
That's 10.
10. 10 times 2.5 would be what?
25.
25 cut in half would give me a front base of 12.5. Okay, now how about the height? The height is the distance between the two bases. What's the height in this? Yeah, you said your base was the front, so we're talking about the height is the distance between the two bases, or front to back in this case. So 4.2 is my H. You guys tell me what I'm going to do to try and find the volume now.
You times 4.2 by 12.5.
You times 4.2 by 12.5. So my volume is simply going to be 12.5 times 4.2. Don't have a clue. 52.5. Okay, 52.5. How do you want to label that, kids? Cubic meters. I love it. First thing you're always going to do is find the area of your what, kids? Base. And then once you know the area of your base, you're going to find the height. And then once you know the area of the base and you know the height, your volume simply becomes the product of the two. Okay? But you have to know what kind of prism you're working with. Okay? All right, so let's take a look at cylinders. Cylinders are unique because what's the base shape of a cylinder?
A circle.
Circle. So capital B is a circle. How do you find the area of circles? We talked about that. Pi times radius squared. Very good. So right here, core concept, kids, pretty important stuff. It says the volume of a cylinder has the same formula. Your volume is equal to base times what? The area of the base times the height. But we know, kids, that in a cylinder, the area of the base is found by doing pi times what?
R squared.
R squared. So we could say that the volume of any cylinder is equal to pi times radius squared times the height. Okay? So take a look at example 3a. Finding the volume of a what? Okay, so my volume would equal, the volume formula for a cylinder, let's write down here, V equals pi r squared times height. Well, what's the radius in this cylinder, kids?
5.
What's the height?
9.1.
Okay, so somebody go pi times 5 squared times 9.1 in their calculator. 714.71. How many can curve? 714. 714. Think they can hear it over there, guys?
No, not at all.
don't think so? Is part B a cylinder?
Yeah.
Kind of, isn't it? Okay, the cross sections, if I would cut a piece across that, what shape would you have? Circle. So it is, it's kind of like this Cavaliers Principle. Now you got to be careful, kids. The height we're looking for is not a slant height, it's still what kind of height here? Yeah, you want a vertical height still. So you guys find the value of this here, okay? Find the value of that right there. We've got that right angle in there. What's the radius going to be in part B?
7.
What are you going to use as height, you think?
22.
Yeah, you don't want slant heights, you still want vertical heights. How tall is it from top to bottom? Measuring from a 90-degree angle from your base. So you guys quickly find the value of that slanted cylinder and make sure you guys agree, okay? Okay, what are you guys coming up with for a value? 3386.6. How many agree? Okay. Bree, you want to walk me through this? What'd you do?
I did 5 times 7 squared times the height 1.
So you've got 3,386.6. Bree, quick question. Were the units okay to start with, or did I have to change anything?
0.
All good. So how do I label this then?
Feet.
Cubic feet. Very good. Okay. All right, guys. Here's what I'm going to tell you today. Things are going to get kind of tricky, but guys, anytime, I want you to remember this. I think finding the volumes is pretty simple for you. What's going to get kind of confusing here is when we start talking about things that are similar and what are their values. Okay. The thing I want you to remember is value is measured in what kind of unit? Cubic unit. Okay. Questions so far in the first 3 pages. Moving forward, kids. So right here, there's a core concept that says the following. I need someone to read that for me. This is pretty important. You might want to highlight this, circle it, do what you need to do, but make sure you understand this, because this is the tricky part, I think, if there is a tricky part in here. Who wants to read my core concept that we're going to look at prior to example 4?
2 solids of the same type with equal ratios of corresponding linear measures, such as heights or radii, are called similar solids. The ratio of the corresponding linear measures of the 2 similar solids is called the scale factor. If 2 similar solids have a scale factor of k, then the ratio of their volumes is equal to k cubed.
It's this last sentence that's really important. If 2 similar solids have a scale factor of what? Then the ratio of their volumes is what? Let's talk about what this even means. You don't need to write anything down. Just pay attention here quickly, okay? Let's see. Okay, I'm going to do this to you. I'm just going to throw a cube here, and I'm going to throw a cube out here. Okay, but what I'm going to do is this. First of all, are they similar?
Yes.
Okay, I don't like the way that they make cubes, and so it looks goofy to me, but anyway, here's the deal. We'll say I have a cube here. Guys, my cube, let's pretend that this here is a 2 by 2 by 2. What would the volume of that cube be? Volume would be 8, okay? Let's say that I say that this is 6 by 6 by 6. Now guys, if I just look at the lengths right here, how many times bigger is each length right here?
3.
3, okay? So what we do is we say there's a side ratio. There's a side ratio that says this. For every 6 units of length here in the bigger one, there are how many units of length over here? Okay, so really the lengths are how many times longer? Aren't they 3 times longer? So what we say is this, they're similar and they have a scale factor of 3. However, when we start talking about volume, things change because we're not comparing just one side, but we're comparing how many sets of sides? 3 of them, right? Okay. Talk about the volume here. You said the volume here was what? 8?
Yep.
What would the volume be here if you took 6 times 6 times 6?
216.
Okay. Do this for me, kids. If I took 8 times 3, would that make 216?
No.
2. Okay. Somebody take 216 and divide it by 8 for me.
27.
So if I take 216 divided by 8, I get 27. Here's what this core concept says. If you have a scale factor of similar shapes, they're saying that the side ratio, in this case 3, helps us find the volume ratio. What we do is we really take 3 to what power? What kind of unit are we talking about again when we measure volume?
Cubic.
Take this 3 to the 3rd power. Tell me what you've got.
27.
Okay, here's the deal. If I go ahead and take a cube right here and triple the lengths, if I just triple all lengths right here, then that means that this will hold 27 times more than the other one. Okay? Think about it this way. Let's say I have a shape and I double all the lengths. How many times more is that going to hold then?
2 times.
Think about it, guys. I'm just doubling the lengths. You got to take that 2 times 2 to what power now? 3. Okay, because you're doubling something this way, you're doubling something this way, and you're also doubling something this way. So how many times are you really doubling? You're doubling 3 different dimensions, aren't you? Think about it. Don't shapes take up 3 dimensions? So if I say the side ratio is 6, and you're saying, oh, well, that means we've got 6 times this way, length, 6 times this way, width, 6 times this way, height. So really 6 to the what power? 6 to the 3rd. We'll hold 216 times as much. Okay? So here's what I want to get at. Let's take a look at the example and see if we can kind of put this into play to help us understand this. Kids, right here, it says square prism A and square prism B, here's the big word, are what?
Similar.
Similar. Okay? It says each edge of prism A is what? And each edge of prism B is what?
6.
It says the volume of prism B is what? Okay, here's what I'm going to do. Okay. We first of all need to establish a side ratio right here. Okay. We're going to establish a ratio of sides for prism A and prism B. Now kids, think about it. It says each edge of the base in A is how much? And each edge in prism B is what? Guys agree?
Yep.
Okay. But then they go on to say, I don't want to talk about sides anymore. They start talking about what?
Volume.
Okay, here's what we need to do. We need to take this side ratio and we need to turn it into a volume ratio. A side is like one length used. But a volume uses how many lengths to determine volume?
3.
So what are you going to have to do to your side ratio right here to get a volume ratio of A to B? Okay, so what we're going to do is we're going to take this 4 to the 6th now, or 4 over 6, and we're going to cube both numbers. So I need someone to run 4 to the 3rd power for me. So, here's my volume ratio. 64 over what? Okay, what this means is this. If the side ratios are 4 to 6, right here, meaning all sides of the cube in the small one are 4 and all sides are 6, that means then, in the small cube, for every 64 cubes I put in the small cube, how many cubes should I be putting in the big cube? Okay, now, let's read the problem. It tells me, find the volume of what, kids? I'm sorry, my mistake. It says the volume of prism B is how many cubic inches? It says find the volume of what? Well, what this volume ratio of 64 to 216 is telling me, it says for every 64 in the smaller one, there are how many in the bigger one? But if you read the problem correctly, it says volume of prism B has how many cubic inches? Okay, so I'm going to set a proportion up here. I want that 135 to go in for prism B. So am I going to put that 135 in the top or the bottom, kids?
Bottom.
So what I'm left to solve here, kids, is this. 64 times 135 over 216. I don't know what that is. How much? Okay. So prism A is how many cubic inches, kids? Listen to me carefully. The first thing you always start out is with what kind of ratio? Side ratio. What do you do to the side ratio to come up with the volume ratio? Cube it. Okay, so this is the ratio we're saying for every 64 cubic units in the smaller prism, there are 216 in the bigger prism. However, the bigger prism has how many cubic inches?
135.
Which means if I just solve this proportion now, that means that prism A would have
40.
Very good. Okay, I want you to try one on your own. Okay, somebody give me a side ratio.
10.
10 to 1?
Sure.
All right, 10 to 1. I'm going to tell you that this is prism A, this is prism B. We're going under the assumption that the two prisms are, what's the word I'm looking for?
Similar.
Similar. Okay, I'm going to tell you the volume of prism B is 8 cubic centimeters. I want you to find the volume of A. How much? Raise your hand when you have an answer. I'll come around and take a peek and let you know if you're right. I can't find a volume unless I have a volume ratio. The only thing, not quite. The only thing I have is a side ratio. What are you going to do to your side ratio to get a volume ratio first? Okay. So the volume now of B is how many cubic units now? 8. So we're saying for every 1,000 in the big, there's 1 in the small. You know there are totally how many in the small? 8 down there, and then just cross multiply and divide, and you got it. When you've got an answer, raise your hand. I'll come around and take a peek. Check everybody's in this row for me. Can I sign? Check these two here. Good.
0, 8.
Good. Good.
Do minimum.
So now you're close.
But in that bottom proportion, you have 8 down here.
No, now you're
Obviously, exceptions.
Jordan.
8. Got it? Got it? All right. How about a volunteer to talk me through this, guys? What am I looking to find right here?
Hey.
Which is a volume, right?
Yeah.
But the only ratio I have is what kind of ratio up here? If I'm going to find a volume, you got to have what kind of a ratio?
Volume.
So help me, kids. What's the volume ratio then?
1,000.
1,000 to 1. Where'd you get that from?
You cube the
10 to the third over 1 to the third. Means for every 1,000 cubes I throw in the big one, I only put 1 in here. Okay? It's kind of like our government. They get $1,000 for every $1 we get, right? Makes you mad, doesn't it, Sonny? Okay, but guys, I told you the volume of B was what?
8.
So am I going to put that 8 up top or in the bottom of my proportion?
Bottom.
Yeah, B is a smaller one, so I put 8 down here. Solve this. What do you end up with?
8,000.
Volume of A is 8,000 cubic centimeters. How many had 8,000? I was walking around. It looks really good, guys. I think you're doing awesome with this. All right. So let's finish up our notes here. Let's see what we need to finish up here. Guys, you're going to talk about finding the volume of a composite solid. Okay. Guys, let's talk about the description here. You guys agree that this looks like a cylinder with a triangle or a prism cut out of it?
Yeah.
So do you guys agree that finding the volume here would be, say, find the volume of the what first?
Prism.
Okay, which prism? The triangular one or cylinder?
Triangular.
I'd always start with the bigger one and subtract out the, and that's going to leave you with the volume of what remains. Here, guys, it says find the volume of the composite solid. The composite solid is this cylinder with a triangular cutout. So this thing is kind of hollow. Can you imagine this being hollow? Okay, so what we're going to do is we're going to find the volume of the cylinder first. Okay, go. Help me do this. Volume would equal what for the cylinder? Okay, how'd you get it? I guess that's my better question.
10 squared times 5 times 30.
Okay. Run that number by me again.
10,053.1.
Now we've got the second part, the triangular prism, right? This is a little tricky. Yeah. 0.1? Thank you. All right, am I good now? Okay, now let's do the triangular prism. Guys, first of all, if I'm dealing with a triangular prism, what's the base shape? Triangle, okay. I'm going to kind of go on this triangle right here. It looks like, I'm going to draw it down here. It looks like we're dealing with a triangle that's 12 on the bottom, is that right? It looks like this is 10 and this is 10 because I have tick marks up here, right? Here and here. You guys agree with that? Okay, so we need to find the area of this triangle. Kids, I'm concerned. We know the base is what here for my triangle? Okay, do we know the height here of this triangle then?
Would be 32.
Well, that's going to be the distance from this triangle to this triangle, but we're talking about just that flat triangle right now, okay? You guys agree that if I drop this in here in isosceles, that would make this 6 right here? Somebody do 10 squared minus 6 squared for me. How much? Now what's the square root of 64? Turns out the height of this, they don't put it in here. We had to use right triangle stuff. Turns out the height is what? So my triangle, the area of the base, would be 1/2 of 12 times the height in the triangle of
48.
and how much are you getting for that? Okay, and then how about the whole height of this triangular prism from here to here then again? Isn't that going to be? So what's the volume of your triangular prism? How would you find that? What was the area of the base? What was the height of the prism? So we can do a 48 and 32 to get the volume of that part we're going to pull out of the cylinder now. Yeah, what is 48 times 32, kids? How much? 1536? Like that? And that would be also in cubic centimeters. So kids, you knew the cylinder, if it was solid, was how many cubic centimeters? And we're taking out how much here, kids? Okay, so what's our total volume then when we're done? How you gonna find that? Yeah, you would do 10,053.1 minus 1,536. Where's that land? I'm not 100% sure.
8,517.1.
8,517.1. Yes. Okay. Find the volume of the big one. Find the volume of the little part you're trying to take out of it. Once you have those two volumes, find the difference and you'll have it. Okay? Yeah, you bet, Cam. All right. Hey, what questions on the notes first? I'm going to hit stop on this. You guys, I haven't sent out an assignment yet, so let me